Well, greetings, Mr. Kolazar's class. We're going to look in today at calculating the Ka's of our weak acids. So we're going to look at how we can get the Ke value given our experimental data of our concentrations of the weak acids. So our memory device, the Rice table, is going to be a useful way of determining our equilibrium concentration. R for the reaction, writing out the chemical equation. I for the initial concentration, change in the concentration, and the equilibrium concentration are the four letters that we're going to look at. So to begin with, if we have a strong acid, there are no Ka values for strong acids, and we're going to look into why that is. So we're going to start determining the concentration of a 0.5 molar HCl solution. So first off, our reaction, HCl, aqueous, is going to completely ionize, so that's going to be our arrow showing that we're going to completely go to H plus ions and chlorine ions. Now, initial concentration, 0.5 molars, or molar, and no, before we start, hydrogen ion or chloride ion in solution. And our change in concentration, it completely ionizes, so we're left with 0, and we're going to gain, our change, we're going to lose our 0.5 molar, and we're going to gain 0.5 molar here, and 0.5 molar solution on each side. So our hydrogen ion is going to break into our hydrogen and our chloride ion. So our change in concentration, we're left with no our reactant, and 0.5 molar H plus, 0.5 molar Cl minus. So when we look at finding the Ka value for a strong acid, our Ka is our concentration of the products over the concentration of the reactants. We're going to be left with the fact that this number is 0, so there's going to be no Ka value for strong acids. We can still find pH if we want, because we know the H plus concentration. So strong acids, remember our arrow for strong acids, and then from there, no Ka values. So where our calculations come in is if we were to look at a weak acid. Now our weak acids, remember, are going to show a reversible arrow. Calculate the K value of a 0.5 molar NH4 solution that has a hydrogen ion concentration of 1.7 times 10 to the negative fifth. Now if we were to look at that, Ka values we're going to calculate, so we're going to start out with our equation. NH4, ammonia plus in the solution, is going to have a reversible reaction to produce hydrogen ions and ammonia. Our initial concentration, 0.5 molar of NH4 and nothing to begin with the other. Now what we're going to look at here is we're going to call what we lose here subtract X. So X is how much ever we're going to lose, and over here this is ever how much we're going to gain of our solution. And in this case we're going to be gaining, because this is our hydrogen ion concentration, our H plus, we're going to be gaining in this case 1.7 times 10 to the negative fifth. If we gain that much H plus, we must also gain that much NH3. So as we're going, we've gained that much, so we must have lost it from over here. Now if we were to look 0.5 and then we subtract 1.7 times 10 to the negative fifth, that number is 0.123 1, 2, 3, 4, 5. So when we subtract 0.5 from it, there's not much of a difference. Our answer here is about 0.499983. So it's approximately 0.5. So what we're looking at is not much of a change. Other ones you might have to actually show the change, but for this one we're close enough sig fig wise to get back to our original amount. So now what we're going to do is look at our Ka is going to be our concentration of the products divided by concentration of the reactants. So our products concentration, Ka, we've got 1.7 times 10 to the negative fifth times 1.7 times 10 to the negative fifth. You could also square this if you wanted. I'm just showing it worked out. Negative 5 there. Divided by concentration of the reactants, 0.5. So 1.7 times 10 to the negative fifth times 1.7 times 10 to the negative fifth divided by 0.15. You get a Ka value that's going to equal about 5.78 times 10 to the negative 10th. Less than 1, so this is going to favor reactants. So remember, less than 1 favors the reactants. If we wanted to, we could also use the H+. If we want to find pH, you just use your H+ concentration, which would have been down there. So that's going to be our way of looking at solving for Ka. Remember, Ka you can solve for Kb in the exact same manner, except you're looking at the OH, the hydroxide concentration instead.